Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on antenna. Okay, so for this video, I'm going to continue the discussion on the antenna parameters. Okay, so in fact, this is the last antenna parameters that I'm going to discuss. This video, I will focus when we can consider antenna under near field or far field region. So this will be the objective of this video. This will be the part 15 series discussion on antenna. So guys, if you're keen to know more about antenna, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on antenna. This is my email. If you have any question regards on this discussion, please drop me an email. Or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. I also urge those experts that is in this area, antenna, give me some input. Like for example, what are the things that I have missed up on this near field or far field region? Thanks ahead. Before I continue, guys, I'd like to urge you guys to help me by like this video. When more of you guys actually help to like this video will have a better chances to reach out to a larger audience. So guys, give me a few seconds by like the video now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. As I mentioned earlier on, this will be the last parameters of antenna that I'm going to discuss. This video, I'm going to focus on when can we classify antenna under near field or far field. What are the rules? So this will be discussed in this video. When the signal actually apply to antenna from transmitter, they basically radiate into free space as electromagnetic wave, which consists of electric and also magnetic field. The characteristics of this magnetic field actually vary with distance from the antenna. In general, these fields are divided into near field and far field region, correspond to area closer to or further away from the antenna respectively. The most commonly used parameter to distinguish between near field and far field is the signal wavelength. Okay, so from here you can see that these are the two zones that we actually classify. Okay, basically the field can be either near field or can be far field. So from here you can see that this is actually the divider between near field or far field. Okay, so this divider is actually correspond to the signal wavelength, which I'm going to discuss later on. Okay, the voltage signal that is actually applied to the transmitting antenna, for example, okay, they actually generate an electric field, while the current in the antenna actually produce magnetic field. So in short, the voltage actually help to create electric field, while the current in the antenna actually help to create magnetic field. Okay, so this electric and magnetic field, they actually interact, okay, forming the electromagnetic field associated with the antenna. So basically, in short, you just imagine when they are actually under the near field, you can still distinguish electric or magnetic field. But once they actually so-called escape from the antenna in a distance that I mentioned earlier on, which is distinguished between the near field and far field, then the field will be combined together as electromagnetic field. Okay, the characteristics of the electromagnetic field generate by the antenna's radiation change with distance from the antenna. Okay, for example, the electromagnetic field near the antenna is actually a spear shape. Okay, so imagine this is actually where the antenna. So you can see that the first very instant of release of the energy is actually look like a spear. Okay, so basically as it propagate further away from the antenna, the field become more planar. Okay, as you can see from here, when they travel further away from the antenna, you can see that they actually behave more like a planar. Additionally, the radiation intensity also vary depend on the distance from the antenna, appearing different when measured closer to the antenna as compared to the further away. So basically, in short, you can imagine that when you are actually very near to the antenna, you can see that they actually appear like a so-called a spear shapes. So once they propagate further away, they become like a plane wave. So basically, this is what you can imagine. Under near field, they typically will look something like this. Under far field, they will be looking something like this. Okay, so let's continue. Okay, the area that is so-called adjacent, which means that beside the antenna, is known as near field region. Okay, so this makes sense, right? When you actually see the near, you know that this near is actually near to the antenna. So basically, this area here is actually known as near field region. Okay, so this region exhibit inductive effect and is sometimes referred as the inductive field. Okay, within the near field region, the antenna radiation pattern and field strength vary depending on the distance from the antenna. Okay, so basically what he said that what will be the signal strength, they actually will be vary. Actually, it depends where or how far it is from the antenna. So this is what this want to explain here. There is some disagreement among engineers on the distance up to which the field can be considered near field or far field. A general accept near field can be defined with the following equation. So basically, this is what it means. Okay, so this time imagine that okay, basically this will determine whether is it near field or far field. But there is always a lot of disagreement among engineers. But in short, this is basically one of the so-called recognized equation so-called to classify the boundary between near field and far field, as it mentioned over here. 2D squared over lambda. Okay, so this is basically the most of the. Okay, so what is this? Okay, so in this equation, lambda is the wavelength of the radiation or electromagnetic signal. So basically, this lambda is actually according to the wavelength of the so-called electromagnetic signal, and D is the maximum linear dimension of the antenna. Which part is the biggest? Basically, this is what it means. Okay, another equation for near field distance acknowledged by many engineers, which is lambda over 2 pi. So basically, in short, you can determine either by this or by this. Okay, so it doesn't matter. So this is basically the larger dimension of the antenna. Okay, so basically 2D squared over lambda, or you can do by lambda over 2 pi. So basically, this actually determines so-called this line here. So anything that is lesser, you actually can call it as near field. Anything bigger, you call this as far field. So basically, this is a very simple definition how you can actually classify near field or far field based on either one of these equation. Then from there, you decide whether is it near field or far field. Okay, guys, again, before I continue, I appreciate your help by like this video. And if you have learned something from this video and you are new to this channel, again, urge you to help me by subscribe to this channel. Please also remember to turn on your notification bell. Once again, thank you so much for strong support. Okay, now let me quickly explain under the near field, okay, which is the reactive and radiative. Basically, under near field, you actually have this zone, and later on, I will mention about far field also. So basically, now let me take a look on these two sections of near field region. Okay, the reactive and also the radiative near field region. Basically, in short, you can see that this is number one, which is the reactive, and this is number two, which is the radiative. Okay, so I'm going to explain the key difference between this so-called two zone that is within the near field. Okay, the near field refer to area close to the antenna conductors or within any polarization medium that is surrounding it. Okay, where the generation and emission of electromagnetic wave can be influenced. So basically, in short, okay, under this near field, anything that is near to the antenna, they can actually affect the outcome. So this is what you want to say. Okay, so in this region, the field line remain electrically attached to the antenna means that the radiation absorbed by the adjacent conducting object in the near field detectable will affect the load on the signal generator. Okay, so this is what I mentioned earlier on. Anything that is nearby, okay, so basically, especially for metal part, when they are actually so-called nearby to the antenna, this may affect the outcome. Okay, so in the near field, the electric and magnetic field can exist independently. So I told you here, near field, you can have either the dominant E field or the dominant magnetic field. So in short, these two can actually exist independently. They don't depend on each other. And one type of a field may be misappropriate larger than the other in different sub-region. So in short, it means that either the E can be bigger than M, which is the magnetic field, okay, or the H field can be bigger than the electric field. So basically, either of the case here. Okay, so a very simple example of a near field effect is the change in noise level picked up by a TV of rabbit ear TV antenna. Okay, so basically this I think it's more and more difficult to find this rabbit ear TV antenna. Okay, so basically this is that they look like a rabbit. Imagine that like a V shape here, a V shape antenna here. So when a human body part actually move close to the ear, okay, which is the antenna. Okay, similarly, the sound quality of an FM radio tuned to a distant station may change when a person move within an arm's length of its antenna. So basically, this is what I mentioned earlier on. So any conducting material, when they are actually classified under near field, this may affect the electromagnetic wave. So basically, in short, under the near field, anything that is conductive when they are actually near, this may change the so-called the outcome of the electromagnetic field. Okay, the region that is closer to the antenna is referred as the reactive near field region. So now, okay, I'm going to explain under the near field, you have two regions here. So I'm going to explain this reactive near field region as you can see from here. Okay, so this region, in fact, will be the closest to the antenna. In fact, just right next to the antenna, and this is actually referred as reactive near field region. Okay, so in this area, the electric and magnetic field, they are so-called phase shift by 90 degree. So you actually can see that the electric field and the magnetic field, okay, magnetic field is in blue, the electric field, which is in red, they are actually 90 degree. So basically when E field and H field, they are 90 degree, you can actually determine the direction of propagation. Okay, remember, in order for E field, E electromagnetic field to propagate, okay, the E field and magnetic field need to be 90 degree. Okay, so once they meet this, okay, so this actually make the field reactive. The radiative property of the electromagnetic field in this region are comparatively weaker. So basically, you compare these two fields, they are actually much weaker as compared to the reactive field. The electric and magnetic field are strongest in the reactive near field region. So basically, under this reactive, the E field and the magnetic field, they are the strongest. Remember, when the signal actually move away from the antenna, the signal will be reducing. So hence, the E field and the magnetic field in this region here, they are the strongest possible. In fact, the closer it is near to the antenna, most of the time, they are considered the strongest. So therefore, they are the strongest in the reactive near field region. Okay, so this enables separate measurement of each field. Okay, because you can clearly measure the E field, you can clearly measure the H field, so hence you can so-called separate measure what is the strength of E field or the H field. However, the dominance of one field over the other depend on the antenna type. Okay, so whether it's a H field or E field basically depend what type of antenna it is. For example, in a loop antenna, the magnetic field actually dominate in the near field region. So basically, if this is a loop antenna, okay, which means that you need a current to run a loop. So once the current run a loop, so basically the H field or the magnetic field will be dominate. Remember, I told you that the current will form magnetic field, the voltage will form the electric field. So basically, for this loop antenna, you basically have imagine this is a loop antenna, you have a current that is actually running around. So basically, they will become dominated by magnetic field. So basically, this is what you want to say over here. Okay, the interaction with the medium, okay, for example, the body capacitance, okay, can cause energy to reflect back to the source, okay, that is actually feeding the antenna. So now I'm still at the reactive, which means that the closest to the antenna. So now a lot of time when we actually want to use our iPad or phone, we can use this so-called the body capacitor or the capacitor effect to zoom or unzoom. Basically, this is what it means here. So when we actually want to do some interaction, okay, with the medium, okay, basically, for example, the body capacitor, okay, some energy will be reflected back to the source that is feeding to the antenna. Okay, so as occur in the reactive near field. Okay, so this zone is roughly within 1/6 of a wavelength from the nearest antenna surface. The near field has actually garnered increasing interest, particularly in the development of capacitive sensing technology, okay, such as those used in the touch screen of mobile phone and also our iPad, etc. Okay, although the far field is typically the primary region of antenna operation. Okay, so you keep this in mind. when we actually want to radiate an energy, okay, we actually want to radiate them under the far field. This is what you want to say. Because we want to send the signal as far as possible, or if not, they are so close, there's no meaningful idea to send a signal. So hence, when we actually want to send a signal, we want to send as far as possible. Hence, this is what I mean. Okay, so most of the time, it will be actually under far field. Okay, so basically, these are the typical primary region of antenna operation. Okay, certain device actually specialize for near field communication. Okay, so basically over here you will see a very simple example, okay, which is the capacitive sensing. Okay, so magnetic induction, okay, as you can see in a transformer, is a simple example of this type of near field electromagnetic wave interaction. Okay, another example including the send and receive coil for RFID. Okay, so once you do wireless power transfer, for example, for wireless ID here, for example, okay, or the emission coil for the wireless charging, or and also the inductive heating. Okay, so basically this is how we can actually heat up the water, okay, without really touching each other. Okay, however, their technical classification as antenna, they are actually remain contentious. The electromagnetic field that actually radiate when the electric and magnetic field are actually perpendicular to each other. Okay, so and have zero phase placement. Okay, so now I like to concentrate on radiative, which is further away. Okay, so basically this is what you mean by radiative. So earlier on I talked about the reactive. So now I will mention about the radiative portion here. Okay, so this is basically for the radiative. Okay, so basically the electromagnetic field, they actually radiate, okay, when the E and H field, they are perpendicular to each other, as I mentioned earlier on. And now under this radiative near field region, they have zero phase placement, which means that they have zero phase difference, which means that they are all in phase, which means that they have the maximum number, they also have the maximum number and minimum possible number. Okay, the region where the electromagnetic field actually transit from reactive to radiative is called the radiative near field region or the Fresnel region. Okay, so this region actually lies between the reactive near field and also the far field zone. Okay, so basically quite makes sense. This part is on the extreme left, as you can see from here. Okay, so basically this zone is actually in between the near field under the reactive and also the far field. This is what you want to say over here. Okay, so in this region, interaction with the medium may fail to return energy to the source because this part here, okay, is considered quite far away from the antenna. And because of this, let's say we want to do some so-called reflect the signal back to the antenna. Okay, so some of the signal energy may not be able to do this. So this is what you say here. Okay, so in this region, interaction with the medium may fail to return energy to the source, which means that there is no reflection. Okay, so but can distort the electromagnetic field, okay, deviating significantly from its behavior in free space. Okay, so basically this is what we also call the transceiver into the far field, okay, which is the impedance of 377 ohm. Okay, so if you still remember, this is what we have discussed under the EMC. Okay, but over here, let's me just focus on the antenna. Okay, so this marks the radiative near field region, which is somehow further away. Passive reflecting element can be placed in this zone for beam forming, as in the case of Yagi Udan antenna. Okay, alternative, multiple active element can be combined to form an antenna array where the loop shape actually depends on the distance between element and their excitation phasing. Okay, so basically this is under the radiative near field. Okay, so let's come into the far field region. Okay, the region furthest from the antenna dominated by radiate electromagnetic field is actually called the far field region. Okay, so basically this region actually directly follow the radiative near field region. Okay, so basically this is actually one step after the radiative energy. So therefore, this region, which is the far field, they have more or less, okay, similar characteristics from the radiative near field region. Okay, in the far field region, the radiation pattern of an antenna is actually independent of the distance from the antenna. Basically, once you reach the far field, okay, the radiation pattern, okay, of the antenna, how it look like, okay, basically they will be independent. Okay, whether is it very directive, etc., they are actually independent. Okay, where you actually away from the antenna. okay, the radiation effect is actually more pronounced here because the E and magnetic field, they are actually orthogonal to each other. And the direction of propagation resemble that of a plane wave. So basically, E and H field, they are actually 90 degree. Okay, so basically, they are 90 degree to each other. And basically, if you still remember the right-hand rule, you actually can determine the direction of propagation. Okay, the strength of the field in this region can be calculated using this fringe formula. Okay, when designing antenna or working with antenna interface system, it is always very important to understand the distinction, the distinctions between the near field and far field. Okay, so this is very important. Okay, as I mentioned earlier on, okay, you need to classify firstly where is the near field, where is the far field with the two equations. So this is very important. So after that, once you conclude that it's under far field, then you will look at this stack of so-called information to understand the characteristics. Okay, when the antenna so-called radiate the electromagnetic field that actually fall under this far field region. Okay, so in contrast, okay, the far field is the region where the field has stabilized into normal electromagnetic radiation. So basically, once the wave actually reach the far field, okay, so the field more or less will be stabilized into normal. So basically, so-called will be as usual, the electromagnetic radiation. In this region, it is actually dominated by the E or magnetic field with electric dipole characteristics here. In the far field region of an antenna, the radiate power actually decreases with the square of the distance, and the absorption of radiation does not feed back to the transmitter. Okay, because they are already very far, so therefore the absorption of radiation, they will not be able to feed back to the transmitter. Okay, so in the far field region, the electric and magnetic field component of the electromagnetic field are actually independent. Okay, each is produced by change in the others. The ratio of the electric to magnetic field intensified basically will be determined by the wave impedance of the media. Okay, for example, let's say the wave impedance of the media, which is air, okay, which means that it's actually 377 ohm. Okay, also known as the radiation zone. Okay, so basically you know that under far field, basically they concentrate how to radiate further and further away. Okay, so the far field exhibit a relative uniform wave pattern. Okay, so this zone is significantly because far field generally actually decrease in amplitude as 1 over lambda. So basically, this is not for the dominate one. Remember, I told you that the E and H, there will be a dominate field. So basically, the one that is actually not dominate will be reducing in the rate of 1 over R. Okay, so basically, this is what I mean. The total energy per unit area at a distance R is actually proportional to 1 over R squared. Okay, since the area of a sphere is actually proportional to this, the total energy passing through the sphere remain constant. Okay, this implies that the far field energy propagate outward to infinite distance, which means that they actually radiate. So from here you can see that under this far field, the key thing is how to radiate the energy further and further away. So basically over here in this video, you learn how to determine when the antenna fall under near field or far field region. And I have also explained under the near field, if you still remember, there are actually two zones. Okay, one is the reactive, another one is actually the radiative zone here. So basically, in near field, you actually have two zones. As for far field, most of the time, this is actually the air. So the impedance of the air, which is about 377 ohm. Okay, so basically, this region is mainly how to propagate the energy as far as possible. Okay, so basically, with this, okay, I'd like to end my discussion. Okay, please help to like and subscribe. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you.